Okay, well, welcome everyone. I want to welcome you to this week's Nano Exploration Seminar. So today's speaker is Emma Batson, who's going to be talking about superconducting nanowire electronics in magnesium diboride. I'm Carl Berggren. I have the good fortune of being Emma's advisor. And Emma is a fourth-year grad student in the group. She is an NSF graduate research fellow, and she's worked on a couple of projects over time, all related to superconducting materials in one way or another. And so I'm very happy to host this. A couple of quick housekeeping points. If you have questions during your talk, we won't be able to answer them during the talk, but go ahead and enter them into the chat or into the Q&A, or raise your hand and we'll get to them at the end. So with that, I'd like to go ahead and welcome Emma Batson.
Thanks for the introduction. I'll jump right in. Because I know that not everybody here is familiar with superconductors, I thought I would start with a quick discussion of how our devices work. The main principle is that we actually use the superconducting transition of our nanowires as a switch. So superconductors can switch through temperature, current, or field. How it might look if we used the temperature transition as a kind of device level information is that when the device is cold, there's zero resistance, and we could treat that as a kind of zero state. But then once it's warmed up above a certain critical temperature, now suddenly we have all of this resistance and we have a measurable voltage. So that could be treated as a one state. But for a number of reasons, using this thermal transition wouldn't be very great for devices. It would be slow and not very high signal. So what we usually use in a device is a switching current transition. In this case, when a current below a certain level is applied to the device, the current can pass through without any resistance at all. This is actually kind of a bad example in this plot because this device was fairly heavily shunted. But normally, the line in the middle would just be straight up and down. And so we can pass current through without getting any voltage whatsoever. But then once the current rises above a certain amount, we suddenly enter this resistive regime, and all of the current that was being applied now is shunted into voltage. What this looks like for a practical device, our kind of main focus is on superconducting single photon detectors. What happens is we bias the device to a current just below what would cause it to switch, such that even a single photon hitting the device is enough to cause a small region to switch into that resistive regime. As a result, we get this nice sharp voltage pulse before the device relaxes back into the superconducting state. This has a lot of potential applications in fields like dark matter search, biomedical imaging, or astronomy, anywhere that we have low signals of low energy photons, and we want to detect them with very little noise. One way in which these detectors improve over something like a silicon-based detector is that silicon is actually transparent in the near infrared. So these devices can detect photons that silicon simply cannot. So for that reason, we're very interested in these detectors. And fortunately for us, we also have some compatible logical devices that can work in exactly the same platform. We have the nanocryotrons that work kind of on the same principle as our detectors, but instead of switching them with a photon, we actually switch them with a controlled current pulse that we inject intentionally to perform logical operations. And similarly, we have a device that works on the thermal switching called a heater nanocryotron. And with these three-terminal switching devices that have kind of transistor-like operation, we've actually managed to create superconducting memories and logic that could potentially be used to read out these detectors in a scalable way, all within the cryostat and on the same platform, so with very little losses of our information. However, the typical nanowire device materials that we've previously explored are pretty limited to a very specific family of kind of transition metal nitrides and silicides. While these devices in these materials are great for a number of reasons, they're fairly limited by the low gap, which leads to a low transition temperature, and the fact that they're almost always these amorphous or polycrystalline films. At first, this may not seem like maybe such a bad thing, but when we consider, for instance, that our current dynamics are actually dependent on temperature, the closer we operate our device to the transition temperature point, the less we have these really dramatic hysteretic switching shapes to our current voltage curve. And so that really degrades the device performance. So we want to be able to operate our devices pretty much as cold as possible relative to the transition temperature. A good rule of thumb is that it's pretty tough to operate these devices at, let's say, more than half of the transition temperature. And the materials that I was talking about, that tends to be 4 Kelvin operation or even less. And to get to 4 Kelvin, we need these expensive and energy-consuming compressors and very high-quality heat pumps in order to reach these temperatures. And that really limits right now the deployment of these devices. That limits the kinds of places that might be able to operate such a system. But state-of-the-art cryostats can get 35 Kelvin operation with just something that sits on a table and plugs into normal wall power. So with the cryocooler technology advancing, we should be catching up to take advantage of these new cryocoolers. If we could operate at 35 Kelvin, then we could use a device like this, and we could deploy our devices much more widely. That's where magnesium diboride comes in. It's a superconductor with a transition temperature of 39 Kelvin. So it would be a challenge to operate this at 35 Kelvin, but it's within the realm of possibility. We can at least hope to operate it at 20 Kelvin or so without any heroic efforts. It also is a good material because it has a high critical current and high critical field. Part of this comes from the interesting fact that it actually has 2 distinct gaps, the larger of which contributes a lot to the high transition temperature, while still maintaining superconducting behavior that is understandable within common models of superconductivity, namely BCS theory. So we've found some collaborators at Chalmers and JPL that can give us different kinds of magnesium diboride. So we have a very large space that we can explore with this material. At Chalmers, they specialize in hybrid physical-chemical vapor deposition, or HPCVD. This provides magnesium diboride with the best properties, very close to bulk, sometimes even better because of strain in the film. But unfortunately, it's slow to grow, and we can really only get, a 1 centimeter square piece, a handful of those at a time from them. We're also working with a group at JPL that's learned how to magnetron sputter magnesium diboride, a more similar technique to the way that our silicides and nitrides are usually grown. We have some compromise on the film properties in this case. The TCs tend to be lower, maybe more like 35 Kelvin, but it does allow wafer scale deposition, and that can give us a lot more space, for instance, to iterate on our fabrication processes. And that's important because fabricating devices in magnesium diboride is extremely challenging. It's somewhat easily corroded by moisture, and that can be moisture that's present in hygroscopic solvents like acetone. It's not very easy to reactively etch. It has a very different chemistry than the transition metal nitrides and silicides that we're used to trying to etch. And as a result of these challenges, although people have successfully made single photon detectors in this material, they're very often one-off events. People rarely report multiple detectors made with the same fabrication techniques. And so there's a huge need for scalability and reproducibility of fabrication in this material. And Nano gives us a great opportunity to work on those things. So first, I'll talk about our efforts with epitaxial or HPCVD films. And this collaboration is a bit older, so our results here are a bit more developed. And particularly what we've made with these films are wide wire superconducting nanowire single photon detectors. Not really nanowire anymore, more like microwire, but that SMSPD isn't quite as catchy. So the fabrication process that we used for these detectors involved first encapsulating our films with a thin layer of silicon, and then using an e-beam resist as well as a charge dissipation layer, we favor Electra 92, and using e-beam lithography with either the HS50 or the F125, depending on what we're trying to do, to pattern our wires. We can then rinse off the charge dissipation layer and we do a cold develop. And we used the argon ion mill in Lu Chao Lu's lab to do the pattern transfer to magnesium diboride. This is under construction. We're no longer really using this fabrication process for our device patterning. We're working on bigger and better things, mainly looking at improving our encapsulation, looking at better resists for the pattern transfer, and ways to use the Samco mixed RIE ICP that's in Nano for the pattern transfer instead. But that's all coming soon. The final step that's interesting and a little bit novel in this fabrication process is a sort of post-fabrication step of helium ion exposure. And we do this in the Zeiss Orion tool in Building 24. It has an atomically sharp tip that can excite a very narrow beam of helium ions at about 20 to 30 keV, and we scan this over our entire device to give it a uniform irradiation of helium. This has been done for other superconducting materials such as niobium nitride and polysilicide, and actually found to improve the performance of the detectors as a result. When we do some simulation of this to get insight into what's going on, we see that indeed a lot of helium ions can make it through the resist, collide in our film, and actually embed themselves somewhere in the substrate. We compute that about 1 in 50 helium ions is colliding with our superconducting thin film. You may be wondering, why does that make the detectors better? And that's exactly the question that we've been trying to answer with STEM and other techniques within Nano. But the theoretical hypothesis is that each of these collisions can create a single point defect. It displaces one of the magnesium or boron atoms into what should have been a vacancy. So this defect pair is a vacancy interstitial pair. As a result, the microstructure is locally changed in some ways. It's made more defective. It might seem odd that that would make the device performance better, but in the case of our wire geometry detectors, what we really want is to have as great a percentage of the device very close to being switched. So if there's one point that's constricted, then the whole device is limited to being biased at a lower level. If we can introduce a uniform film of defects everywhere that floods out these native defects, then perhaps that's actually sort of bringing the whole wire down to the same level as the original worst part. And that increases the uniformity, letting more of the detector participate in detection at a given current bias level. So we can also simulate that there's a difference in effective dose depending on encapsulation. So you may have noticed that in my fabrication process, I never actually stripped the resist. This is because of concern about what harsh solvents that can take in a lot of water, like NMP and acetone, might do to the sidewalls of my film. However, this is definitely going to change the effect of the helium ions, whether you choose to do that or not. The resist layer actually slows down the ions, leading to up to 3 times more vacancies predicted in the magnesium diboride that had resist on top. So here we can see this line is the depth within just the superconducting film of the magnesium diboride that was encapsulated. This line represents the magnesium diboride that wasn't encapsulated. So little choices like this in the fabrication can make a huge difference to post-fabrication techniques like helium ion irradiation. So all of that said, let's take a look at what actually we get. What are the results when we expose magnesium diboride that's encapsulated in this way with helium ions? I don't have a plot showing the negative, but just take my word for it that before irradiation, this detector was completely insensitive to light. We put tons and tons of light down the fiber optic into this device, and absolutely nothing happened except that it got a little bit warmer. Post irradiation, we actually sort of irradiated it too much, leading to a pretty major suppression of the transition temperature. But at about half of the transition temperature, we still have this nice IV curve that has this dramatic transition at the switching point. And indeed, we're able to get counts. We get up to 1,000 counts per second with 100 dark counts per second at 1550 nanometers light at 10 Kelvin, which is half of the transition temperature. This is for a 1 micron wide wire that was irradiated to a dose of 1 × 10 to the 15 ions per square centimeter. Another thing that's interesting here is that we actually get these relaxation oscillations at a much faster rate than our maximum photon count rate. This sort of indicates that the efficiency of our device is not so good. It could count faster. The dynamics can go up to higher speeds, but we're not able to get enough of the device sensitive to measure that many photons. So our sensitivity is maybe a little bit low, but our material is still pretty good. It still has these fast dynamics. And one thing, oh, and this work has been accepted to IEEE Transactions on Applied Superconductivity, so keep an eye out for that. And some results that were even better were on helium-exposed magnesium diboride without encapsulation. So in this case, at an even higher dose, so 5 × 10 to the 15 ions per square centimeter, we actually see that the transition temperature is affected very little. So if we get the correct dose, then the sort of broader properties of our detectors are largely unchanged, but they still go from being insensitive to light to counting photons at up to 20 Kelvin. Again, we see this count rate of 1,000 counts per second, and we also have a very fast pulsing behavior. So again, our efficiency may be limited, but our detector dynamics are really fast, and we're able to go up to really high operating temperatures. So this is very exciting. And the next step, as I see it, is to explore this hypothesis of why the irradiation is improving our results. And this work has been accepted to Nature Communications, so keep an eye out for that as well. So we took these detectors and we prepared a lamella from them to explore in the Themis. And what we find is really striking, actually. So on the epitaxial parts of the film, some of them remain epitaxial, and we can actually see the single atomic resolution in these areas. However, to the left of this image, there's no single atomic resolution at all in the magnesium diboride layer anymore. And we attribute this to the helium ion irradiation amorphizing this part of the film, which is in line with our understanding that it's introducing these defects. It's damaging the lattice structure. So that's good support that this is what's going on here. Another great thing we can do with the Themis is look at where the different atoms are located with eels. So if you're familiar, EDS allows us to see magnesium, and EELS allows us to see boron. Unfortunately, it's very difficult for us to see both atoms at the same time, but magnesium loves to oxidize. So the location of the boron atoms is actually a really good proxy for where the magnesium diboride thin film originally was. And the location of oxygen is a good proxy for what has oxidized and where the magnesium may have diffused out of the film and oxidized instead. So what we can see here is that we do still have a really clear stripe of boron where it should be. So this is again evidence that the atoms are moving around as a result of irradiation, but they're not getting kicked out of the film or anything like that. But the other thing that's striking is that we do have these oxygen-rich layers strikingly above and a little bit below the boron. So we can kind of tell from that our encapsulation may not be good enough right now. We are losing some of our film. So that's one of the reasons why we want to go back and improve our fabrication techniques a little bit. And that's really been enabled by these STEM characterization studies. So that's all for the wide wires on epitaxial films. I think the work we've been able to do there is really exciting, but at the same time, it points to some limitations in our fabrication processes that could be better suited to exploring with large batches of films, such as the magnetron sputtered films. So I'll talk a little bit about these just briefly. We've also done some STEM interface studies of these films. We confirmed what our collaborators told us, which is that it's about 30 nanometers capping layer of boron on top of 40 nanometers magnesium diboride on top of 30 nanometers of silicon nitride. The reason for the silicon nitride is that, again, magnesium loves to react with things. If it's sputtered directly onto the silicon, then a large quantity of silicon will tend to migrate and react with the magnesium. We can also confirm through, again, EDS in this case, that indeed the silicon nitride capping layer is protecting us pretty well. The magnesium remains really well localized within the magnesium diboride layer. In this case, I guess I wasn't able to get a silicon signal, but the nitride and the oxygen have also kind of stayed where they belonged. So this is all indication that this magnetron sputtering technique does work pretty well and produces pretty clean films. So thanks to Fabulous, we've been able to plan and prepare some pretty crazy long fabrication techniques that allow us to keep the film encapsulated as much as possible. So we really appreciate the use of this tool for helping us visualize, how well our film is protected at any given point. And we've actually managed to go through our first run of this new fabrication method and create some devices. And we're actually undergoing testing of these devices right now. So we're pretty excited to see where this leads us with these new magnetron sputtered films and to iterate on this fabrication technique going forward. Future directions are going to include continuing the STEM studies, particularly comparing irradiated to non-irradiated films, and looking at more STEM of these sputtered film lamellas to make sure that we're looking at really the best possible technique there. We also need to work on this fabrication technique a little bit. Not all of our devices come out. This one in particular is an example of a device that was incredibly over-etched, so that they don't all work. We need a few more iterations to improve the stability and reproducibility here. And we're also exploring other characterization methods that would help us figure out what's going on a little more easily as we're going through the fabrication, such as trying to develop a vasoipsometry model for these films, which is quite challenging because magnesium diboride is quite anisotropic, and we don't have a model for it or for the boron capping layer. So as you can see from these fits, we've had some progress on this front, but the model isn't the best. So I'd like to thank everybody in the group, but especially Ilya Chureyev for the original magnesium diboride experiments, Francesca Encalza for ion irradiation, and Audrey Jacquiat for device design and fabrication assistance. I'd also like to thank all of the MIT.nano staff. We made great use of the facilities for all of this work, but especially Aubrey Penn for STEM assistance and Juan Ferreira for Delian assistance. Thanks for listening to my talk. I'll take any questions.
Okay, well, thanks, Emma. That was great. So We have plenty of time for questions, so please go ahead and put them in the chat or the Q&A or raise your hand. I'm not sure. Don't see any hands raised yet, so I think I'll start it off by asking. So you showed. Could you flip back to the eels data? So you mentioned that there was boron, and I'm trying to line up the EDS pictures below, or sorry, the eels pictures below with the TEM above, and you see this interface layer. So the first thing I'm wondering is that interface layer just silicon carbide, or is there something else in there?
Yeah, so it's a little hard to tell. Unfortunately, the eels detector is a different detector than the one we get these really nice images from. So I don't have anything that quite exactly lines up these single atomic resolution images with eels in particular. I think I believe that based on the scale of things, the magnesium diboride layer was quoted at being 7 nanometers thick. So I think that the interface layer has to be affected by magnesium diboride. Otherwise, we're kind of missing some material. I think it's possibly, if we look at eels, we can see that there is this layer below the boron that looks sort of oxidized or something. So it could be that this is kind of a magnesium mixture on top of the silicon carbide. I'm not exactly sure. It could also just be that it's magnesium diboride with a kind of weird lattice going on. Yeah, I've thought about it, but I don't totally know.
Okay, great, thank you. So we have some questions now in the questions and answers section. Thanks everyone for putting those in. So let's start with Changsub Kim. Changsub says, maybe I missed it, but what kind of vacancies, atomic, like Mg or B, are you creating when you irradiate with helium ions?
That's a great question. So because we don't expect these atoms to leave the film, we expect that they're knocked out of their original lattice position, but they remain within the film. It would be a little hard to tell with compositional techniques like EELS or EDS. I believe that because the boron is lighter, it's probably more prone to getting knocked around. And I think we could probably double check our simulation data to see if that's what we would expect. But I think it would be kind of tough to experimentally confirm which it is. It's a great question. I'd have to think about it.
Yeah, Changsub suggests that maybe we could use XPS to check the valence states of the residual films, as you bore down, which is an interesting idea. So I
That's a great point.
wouldn't know how to do that, but maybe now we know who to ask for more information.
Oh, I actually do have XPS experience. I used it a lot for the ITO project.
Mhm.
I just hadn't thought about it in a
Well,
while.
yeah, I guess right. Yeah, I think that the question is sort of what are the valence states that tell you whether it's magnesium that's missing or boron that's missing, I guess. So Oded Rabin asks a second question, which is, I think you started, yeah, their first question. I think you said that this type of single photon sensor has a lower dark signal than other types. So why is that?
It's pretty stable, I believe. So the main limitations are the stability in your operating point. So if you can extract a really stable current, then your operating point will be quite stable. If you're operating at the base temperature of a particular cryogenic system, so where it's designed to hold at, then in that case, the temperature component of the operating point is usually very stable as well. Part of the advantage comes from operating it at a cool temperature. So due to the cold operating point, we're going to have less thermal photons that are going to confuse the noise. So to some extent, if you're really trying to minimize the dark counts, you actually don't want to operate it at a higher temperature. in operating it at a higher temperature, we would be having some trade-off in the dark count rate, but we still get these other advantages like the ability to detect single photons in the near infrared and having very fast reset times.
Yeah. So I think you're, maybe to paraphrase that, just the fact that we're able to operate at a lower temperature helps us in terms of the dark count rate. Yeah. Okay, so then there's a question here that says, can you comment further on specifically what's improved in the new fabrication method compared to before?
Yeah, so I think a lot of the complication that you see here is efforts to keep the film encapsulated more thoroughly. Uh, so we've tried very hard to make sure that we're using a hard mask so that photoresist never has to come in contact directly with our film. After we mill the sidewalls, we're re-encapsulating it with silicon nitride, which again, as we established with STEM, is going to result in very little diffusion into the film that could damage it. I've put ion milling here in this particular iteration, but we've also been exploring ways that we can do the pattern transfer using the RIE-ICP tool, which is nice because that would allow us to do everything in the clean room. It's also a load locked tool, and if you have some chemistry involved, you have a little bit more ability to determine the selectivity. So it's kind of a complicated answer, but I think the short of it is just trying to understand a little better the chemistry of this material and how we can take advantage of that, as well as trying to really minimize the contact our material makes with solvents and air. Those are the main changes here.
Great. So then there's another question here from Changsub, which is, can you sweep through the frequency or wavelength of the photons to check the threshold, presumably as a way to kind of understand the material?
Like for the detection?
I'm assuming, yeah, that's what he means.
I think in theory, yes. In principle, it's a little hard just because, you get your optics set up, it's kind of optimized for one wavelength. 1550 nanometers is the longest wavelength that we have on site. We also do some testing with 780 nanometers or even UV, I think like 440 or similar nanometers. But to go much longer than 1550, I think the setup becomes a little more challenging. So it's something that in principle we can do, but in practice, it would kind of be a full study on its own, I think, to get the apparatus set up to perform an experiment like that. It could be worth it, but I think it's not what we've been focused on so far.
Great. One, we have a question from Shubhankar Hussain, who says, in the magnetron sputtering fabrication process, there was also a boron layer on top of the magnesium diboride layer. What is the purpose of that?
Yeah, so hmm?
Yeah, go ahead. Sorry.
So this actually is kind of a result of the way that the group at JPL does magnetron sputtering. The boron layer on top is actually required to sort of maintain the stability of the underlying film and to maintain a smooth surface of the magnesium diboride. While they have to do a post annealing process to improve the uniformity. It's actually a very interesting technique where they sputter these different layers alternating of boron, magnesium, and boron, and then they anneal it all together into the magnesium diboride layer. As a result, they require a layer on top to prevent evaporation of different atoms off of the surface, I believe. I might be, I'm paraphrasing this myself, so I hope I haven't misrepresented the process, but I believe it's a sort of protective thing for the various steps of their sputtering process.
Great. All right. Well, thank you again, Emma, for the very interesting presentation, and to all the participants for their questions and attention. I want to just, before wrapping up, mention that the next nano exploration seminar is going to be on May 14th, and it's going to be given by Giuseppe Romano from the Institute of Soldier Nanotechnologies. And this presentation is going to be posted at the Nano Explorations website after it's been edited and captioned and so forth. So with that, thank you everyone, and we'll end the session.
Thank you.